Today's presenter is Josué Melguizo-Gavilanes. He received his PhD in mechanical engineering from the University of Calgary in Canada in 2012. And then he worked as a researcher for Royal Dutch Shell before going to the Caltech, California Institute of Technology in USA, where he was a senior postdoctoral scholar in aerospace. Josué is currently a CNRS research scientist at l'Institut Pprime in Poitiers in France. He's part of the Fluid Thermo and Combustion Department in the Detonations branch, working on fundamental and applied combustion research, including shock and thermal ignition, flame propagation and acceleration, deflagration to detonation transition, detonative propulsion, chemical kinetics, and hydrogen safety. So as you've heard, his research experience is quite diverse and encompasses computational fluid dynamics and analytical modeling of reactive flows, which he's put to use in successful collaborations with experimentalists. He provides complementary expertise on numerical and theoretical modeling and experimental techniques, which they apply to reactive flows at l'Institut Pprime. Today, Josué is going to be presenting dynamics of detonation transmission and propagation in a curved chamber, a numerical and experimental analysis. The talk will be recorded, edited, and posted on our website, which I'll post in a second. And once the speaker approves the final version. On the website, you can find previous talks and information on upcoming talks also. So if you have any questions, I encourage you to ask them in the chat where we'll be monitoring. Josué said he doesn't mind questions throughout the talk, and he might stop to collect them in a sec. Otherwise, we'll review them all at the end where we can have more presentations. So without further ado, Josué.
Well, thanks a lot for the introduction, Shem. That is very nice to be able to interact, and I think this is a wonderful initiative that you guys have put together, Xiaoxin and yourself and all the people that have been collaborating in this. I know it's not an easy task to get people together, especially online and all these things, but it's great that we have an opportunity to discuss now that we do not have the ability to meet each other in person. Well, as Shem said, I do not mind taking questions during the talk. I understand that it will be a bit difficult during a presentation that is given online, but I mean, we'll try. If not, we can have just the formal discussion at the end. I want to, well, I mean, this first slide, Shem already described. So that's my current affiliation. I work at l'Institut Pprime, but I'm a CNRS researcher. So in France, things are a bit, in terms of how research is organized. So this Institut Pprime, it's a big research institution that takes people from the CNRS, the University of Poitiers, and the School of Engineering. I happen to sit at the School of Engineering, but I'm officially a CNRS researcher that depends directly from the government. But I provide my services and my research expertise at the School of Engineering, but we all belong to the Institut Pprime. As you can see, there's a bit of bureaucracy there. Anyway, so where is Poitiers? I'm going to start with a brief introduction also about myself and what my research interests are before I get into the main topic of this presentation. So Poitiers is actually right here. If you can see my cursor, Poitiers is in between Paris and Bordeaux. And then the lab, the Institut Pprime, is actually 15 kilometers north of Poitiers. So it's a very nice place. It's a relatively small city, but it's very nice. And we have state-of-the-art experimental and computational facilities there. So it's a nice place. This is what it looks like, a picture from, this is the School of Engineering. So that's ANSMA. The Institut Pprime, as I said, comprises l'ANSMA. And then I sit in this building, and then my actually employer is the CNRS, which is the National Research Institute in France. And this is l'École Nationale Supérieure de Mécanique et de l'Aérotechnique, which is the place where I sit. And this is just a view of the campus from there. Now, I'm going to introduce myself now in terms of what my academic and professional research experience has been, what my research interests have been so far, and how do they all fit together, and why I'm interested in studying what I'm studying. So as Shem mentioned, I have 10 plus years of academic and industrial research experience. I'm currently a chargé de recherche, which is the equivalent of a research scientist at the CNRS. Before I was a senior postdoctoral fellow, I was working on thermal ignition under the supervision of Joe Shepard. Before that, I worked for Shell. I was looking into some field data and trying to model that in baffled reservoirs in the Canadian North, so in Peace River, Alberta. And then before that, I was doing my PhD under the supervision of Luc Bouwens. I was looking at some theory and doing some numerical simulations of shock-induced ignition and looking at the effect of the kinetics on the dynamics of this ignition. And then before that, I was a visiting scholar at a summer intern rather at KIT, which is an institute in Germany, working with Maya Kuznetsov. And before that, I did my undergrad in Colombia, which explains the Spanish sounding name that I have, Josué. All right, so with regards to research interest so far, so the overarching picture is accidental combustion events. And how does a typical accident happen? So you typically have a combustible mixture or a fuel release, right? So that could either be premixed or non-premixed. And that's, I actually did some work on fuel releases during my postdoc. And then depending on the pressure levels, you typically ignite that mixture in two very distinct ways. You can either go through a thermal ignition process, in which is just a hot surface or anything that the fuel could be exposed to, and then you typically initiate a flame, and then you go through this way where you have flame propagation, then the flame accelerates, and then you get into a detonation to detonation transition scenario. And then you have a detonation that propagates. Or depending if you have a high pressure release, you could actually ignite directly a detonation, right? Now, with regards to detonations, so the main motivation before I went before I joined the CNRS and Institut Pprime, it was safety. But then there's a strong wealth of knowledge and facilities at the Institut Pprime in which we could actually harness the high energy release rate that we have in detonation and potentially use it for propulsion. So I've been involved in some of those efforts there. And as well in looking at detonation to detonation transition, deflagration to detonation transition rather, and really on the fundamental side of things, in particular with smooth channels, in which you have many potential ways of reaching this detonation onset, because you have boundary layers that form that are of the order of the characteristic length of the channel. So you can have choke flame boundary layer interactions or just simply shock ignitions. And you can also have, typically when you have obstacles, then I would say there is more or less agreed in the community that the most likely way of initiating a detonation is through shock-induced ignition. So if you can see, I have contributed and worked a little bit in all of these different aspects that are involved in an accident scenario. Now we're going to get into the actual material that I'll be presenting here. So I'll start with a little bit of a combustion refresher, just to make sure that for those that actually joined the presentation that may not be super familiar with detonations, to look at the two different propagation mechanisms that we have of traveling waves in reactivepedia. And then I will just in the normal way motivate, go through the experimental and computational methodology, look at some results and discussions, and then I will close my presentation. So as Shem said, I'm going to be talking about detonation dynamics in a curved chamber. This is a numerical and experimental study that I carried out with Vincent Rodriguez, Pierre Vidal, et Khatiba Situn at l'Institut Pprime. I've been very lucky to have been able to work with them because they have vast expertise in this. And I just came in with the computational part and tried to contribute to a lot of work that they had already done. As you can see from all this close to 10 references in which they've been working on fundamentals and transmission and propagation limits, and in particular looking at a very interesting regime that we'll discuss in detail later. So as I said, a little of combustion refresher. So typically most people are familiar with deflagrations, right? Flames that we encounter in our daily lives. So the propagation mechanisms for a deflagration is typically heat and mass transfer. So you have hot products, you have a time scale of diffusion of heat, a time scale of diffusion of mass, and then this brings the temperature ahead in this region that we call the preheat zone, ahead to a temperature high enough so that you activate chemical reactions, and then that just keeps going and you have a front that propagates, right? So the propagation physics for deflagrations is heat and mass diffusion. Typically in the conventional sense, if you have slow or the traveling wave, what we call the burning speed, the pressure is typically constant across the interface. You have high temperature, hence low densities, and then the steady velocities, the laminar burning speed, as I said, is of the order of meters per second. Now, when we have the detonations, we have a completely different story. So you have a shock wave that we show here. So temperature and pressure increases across the shock wave. And then it's really adiabatic compression by a shock wave that activates the chemistry behind this front. So you activate the chemistry, then if you follow this red line, you see the temperature increase, and then the pressure decrease. So you compress, ignite, and expand just behind this reaction zone that is depicted by this green line there. So as I said, propagation physics is very different. So you compress and then it's really shock-induced ignition. You have, across the interface, you have a rising pressure and density. And the steady speeds, the steady propagation velocity is of the order of kilometers per second. Okay, so 3 orders of magnitude between what the typical steady propagation speeds of flames are compared to detonations. Now, the other thing is, now when you look and you put detonations into a tube and you look at them experimentally, this is what they look like. So you have so this is a schlieren picture of a propagating detonation. You have a very dark interface, which is the shock wave, and then you have all these transverse waves that travel along the front transversely. Okay, and this is a very distinguishing feature of detonation. So it's this transverse waves. So this is the 2-dimensional, or experimentally what you would observe if you were to take a picture of a detonation inside a tube. And one of the interesting things is that they propagate remarkably at a constant speed. Right, so what I was saying right here is that we have, even though this looks as a very planar front, if you actually zoom into this, you have this transverse waves that you see very tiny right here. And then, as I was saying, for scale, this is 30 millimeters in physical length. So if you go and dive into the cellular structure that you see there, then you see these transverse waves and this front curvature. And then if you actually take something that is very peculiar as diagnostics in the detonation community, is to actually have a soot foil inside your tube. You get this very distinguishing features of a detonation, which is what we call the soot foils, or the cellular structure of a detonation. And depending on the chemistry and the mixture that you have at hand, these structures that form are either very regular or very irregular. And the mechanisms of formation I show right here in the bottom plot, that is simply the trajectories of these triple points, that is the intersection of the transverse waves and the front and the leading front that propagates axially, then draws these triple points that follow these trajectories. And when they collide, they activate the chemistry once again, and then you have a repeating cycle of this mechanism. So now that we covered a little bit of the basics of how detonations propagate, what the distinguishing features of detonations are, then I'm going to motivate a little bit why we're interested in studying the detonation dynamics in these curved chambers, and in particular, why we're interested in doing it with hydrogen. So why is hydrogen important? Well, as I said before, we have some safety hazards that we still need to understand, and as I mentioned before, or as you can see, there's been a lot of interest lately in hydrogen. So in any place that we store fuels or handle fuels, there's always the risk of having a leak. And if you have a leak, and you always have the risk of having an accidental ignition, and if you do have an accidental ignition in confined spaces, then that could lead to deflagration to detonation transition, just as I described at the beginning of the presentation, as I was explaining the typical accidental scenario. And then the other motivation for this is that there's been more and more interest in trying to use hydrogen as a potential alternative for carbon-based fuels. So you can use it for ground transportation, for propulsion, for energy production. So there's definitely been a huge push for this. In particular for us, as I think my view is, the safety hazards for very high-risk industries such as the nuclear industry and others like mining or oil refineries and all that, you really want to make sure you prevent this, because it's these accidents, because it's a high-risk industry. And what I mean by high risk is that even one accident could lead to catastrophic consequences in terms of losses of life, infrastructure, and environmental impact. So we want to make sure we understand everything, or at least contribute to the understanding of this, so that we can go forward with applying all these learnings. And then recently, that's why I have the propulsion picture here, is there's been an increased interest in pulse detonations, and in particular in rotating detonation engines, what they call the pressure gain combustion modes, that are supposedly or allegedly more efficient than current propulsion cycles. So I'm now going to go into detonation in propulsion, and in particular rotating detonation engines. So this is a typical example. So what is a rotating detonation engine? Its simplest form is two cylinders, two concentric cylinders. So one of a diameter that is smaller than the other one. And then you inject, and you can actually inject radially as well, or actually that depends on the configuration that you have. But then what you have is no moving parts, a detonation front that moves along the circumference, and then very high pressure behind the front, and then you expand. And that's how you would produce thrust. So one of the advantages of this is that you have no moving parts, compared to other types of typical, turbines, where you have all these vanes and everything that you have to take care of. But there's also issues. And as you can see from this schematic, this is a highly non-ideal flow, right? So you have discrete injection. So you have a non-uniform mixture that is ahead of your wave. You also have mixing between burnt, because these are the burnt gases, these are the fresh gases. So you have mixing. So in addition to having a discrete non-uniform mixture, you also have a layer in which you have partial burning because of the burn gases and the fresh mixture that is ahead. You also have confinement, that has implications on the structures that you see. And you also have three-dimensional effects. But in this particular case, what we're going to be, or at least in my presentation, what I'm going to be focusing on is on the chamber curvature. Now, I'm not going to go into an extensive literature review. I just want to give you a flavor of what's out there, experimentally, numerically, and theoretically as well. And this has been recently, I would say that the last 10 years, there's been an explosion of the amount of work that it's been done or carried out on rotating detonation engines, especially driven by Europe, Japan, the United States, and Russia. And they typically focus on thrust and mass flow rate measurements. So it's what is the optimal fuel to oxidizer ratios, what are the nice or more appropriate injection strategies that we need, what are the downstream flow constraints that we need to put in there. And in particular, Institut Pprime, there's been a lot of work since 1996 on pulse detonation engines and rotating detonation engines. And I do, if you have an interest in this, I do encourage you to search the publications that have been come out of our group on this particular topic. But this is not to say that all the work we do at Pprime has to do with rotating detonation engines. We mostly work on fundamental work, both state-of-the-art facilities, experimental facilities. Same for the numerical resources that we have both on site and at the regional level and at the national level in France. So there's a lot of, this is just one part of the work that we do at Pprime, but it's an important component of the stuff that we do, and it's mostly applied studies on feasibility, on whether this is actually a viable way of doing things. Now, in terms of numerical and experimental work, and there's been from overall combustion simulations in which you integrate your compressor stages into a rotating detonation chamber, to more fundamental canonical studies in which they're just trying to investigate the wave dynamics inside this curve geometries, right? And that's where we lie. In particular, this is work that was published in our group in 2017, which they were looking at the dynamics of this for propane mixtures. So the goal of the study is to characterize the detonation transmission inside a curved chamber. And what I show right here on the left-hand side of this animation is like a typical shot of what happens inside the chamber. But right here, I'm showing CH emission. As I said, we're going to be working with hydrogen mixtures. This is just to illustrate what I mean. So we have initially planar detonation that propagates into a curved chamber, right? And then inside, after you have all this propagation and all these regions of high intensity and reaction, if you do take the soot foil, this is what you have, right? So you have this the cells that I talked about before, and some regions where you have no cells, some regions with cells, and this is a typical experimental diagnostics that is used in detonation research. Now, what do we mean by characterizing the dynamics inside? So by characterizing, as I said, or what I showed before, is we're going to look at transmission, diffraction, failures and reinitiations, and reflections. So you see, initially we have a constant area region where you have the detonation propagating. As it reaches the curve part of the detonation and the area increase, you have a bit of decoupling between the leading shock and the reaction zone. And then you also have failures and reignitions, and then you have reflections along the outer wall. So how are we going to do this? We're going to perform a combined experimental and numerical study for increasing pressure, and we're going to use a highly diluted stoichiometric hydrogen-oxygen mixture. And there are reasons to choose this type of mixtures, and those are tied with the ability to model it with detailed chemistry, and as well with increasing the characteristic lengths that we have in detonation, which will make it more tractable in terms of performing a computational study. And the expected outcome of this would be to learn a little bit more from actually combining both efforts, right? As we know, we can do experiments. We do have limitations in terms of what we can measure. So the plan is to have a synergy, so to have a complementary study where we can learn something from the simulations and vice versa, inform our simulations with some of the experimental work. So this is what the experimental setup looks like. So we have a detonation tube. This is an actual CAD of the experiment. So we have this detonation tube, that is connected to this chamber right here. We have an expansion vessel right after everything ignites and burns inside with discharge. We have a high-speed camera and visualization along this line. It's an inline configuration rather than the typical Z configuration that a lot of people use. We've had very good results with it. And the way a typical experiment is run is you fill the whole entire tube and chamber. This is a detail of the chamber. You ignite with a spark plug. You have a Schelken spiral right here. So we initially initiate a deflagration. We make a transition to detonation. It propagates in the tube to its steady detonation propagation speed, and then it goes into the chamber and propagates and does what it has to do as it goes inside. And this is a more detailed view of what I just explained. So we have this tube, we have the detonation propagating, and then these are the dimensions of the chamber in millimeters and the tube. And then this Mylar tube will come in later. Just keep that in mind and keep this theta angle in mind as well on how we're measuring these angles for some of the results that I will show later. So in terms of diagnostics, we have, we're going to look at chemiluminescence and chemiluminescence of the whole entire chamber. This is done with a Princeton camera with a lens, a Nikkor lens that allows us to actually see very nicely the filter visible light and collect the chemiluminescence that is coming from the reactions taking place. This is a dual frame Princeton camera, so that means that we're only that we're capable of taking 2 pictures per shot. But as you can see in the results that I'll show later, it's quite repeatable, and we can actually have a composite of the whole dynamics. And then for high-speed schlieren, we're going to focus mostly on this region, but I will show results as well for other regions in the chamber. And this is with our newest camera, which allows us to take up to 10 million frames per second. So this is very nice to actually describe and resolve the high temporal dynamics that takes place in this chamber. Now, with regards to the computational methodology, we're going to do a 2D planar reactive Euler computation. So most of you must be familiar with this. So just to reiterate, what we mean by Euler is we don't have any diffusive effects. So we have no heat or mass diffusion. This is, as a result, no heat, no mass, and no momentum diffusion. Hence, it's an inviscid computation. So we're only looking at the gas dynamics and how the gas dynamics couples with the chemistry. As I said, it would be a detailed kinetics mechanism that we're going to couple with the equations of motion, and we use a detailed mechanism that comprises 9 species and 21 reactions, and of course all the thermodynamics is temperature dependent for this type of simulation. We're going to be using OpenFOAM to simulate this. The spatial discretization is using finite volumes, and there are advantages to using finite volumes as opposed to using finite difference methods. We also have a finite difference methods solver in our lab that is called Resonant. But when you have curved geometries, finite volumes are a better candidate to deal with them, because you avoid surcasing and potential noise that might come from the walls if you're not resolved enough. So these are just details on how we compute the fluxes at the cell faces, how we reconstruct. I don't think we need to go too much into details. I mean, if you have questions, we can discuss about this. And all the implementation and the verification of the solver follow the methodology that was presented in a paper by Karpushin, in which they actually looked and developed the coupling of the hybrid, because this is a hybrid solver, that you can actually solve very efficiently flows that are low Mach number, and you can do the coupling very nicely with high Mach number flows. But for the case at hand, we're only using the latter part of the hybrid scheme. So it's standard flux limiting and reconstructions to compute the numerical fluxes. And it's a second order in time and space for the discretization, and the chemistry is a fourth order ODE solver that allows us to do that. So we verified and validated the solver with these two references here. So this is what the initial boundary conditions look like. So we actually meshed the exact geometry in the same exact way as experimentally, except that we just have a planar geometry. We don't have the depth to this, but in terms of the dimensions, we reproduce the experimental geometry as best as possible. And this is something that needs to be highlighted, because this is not typically done in detonation research, that we can actually simulate the full geometry. And there are reasons as to why we can do it, and one of them is the choice of the mixture, in which we have characteristic lengths that are still tractable. But as you can see, we still have 10 million cells in this 2D geometry, and that required about 10,000 CPU hours per case. Now, in terms of initial conditions, we tested 4 different initial pressures, same initial conditions inside when it comes to temperature. And the way we ignited, this is a different approach from what we typically had in the experiment. Of course, we don't want to simulate the whole detonation tube. So we actually imposed 3 hemispherical zones right here in this region at these conditions. So 45, 46 times and 14 times the initial conditions. So we pretty much ignited at detonation, but we made sure that by the time it reaches the start of the curved chamber, it's already propagating at its steady detonation velocity, CJ. And you will see that from some plots that I will show later. In terms of the resolution, so as we increase the resolution, because we kept the number of cells the same, as we increase the pressure, the characteristic lengths of detonations decrease. Hence, the number of points per Z and D length, induction length, will vary from 15 to 5. So we had 15, 10, 8, and 5. Can you guys see the cursor or no?
Yes.
Okay.
Yes, I can. Yeah.
All right. Now we're going to look into the overall dynamics. So what we learned, or what we were able to get at 15 kilopascals. So this is a video of that we got from our simulations. And as I said, the simulations were initiated using the initiation scheme that I showed earlier, but these were done not at the same. In other words, I simply set my initial conditions to those of the experiment in terms of the concentration, the mixture we were going to use. I initiated my detonations numerically the way I mentioned in the previous slide, and I just allowed my computer to work, and this is what we got, right? And then we did the comparisons with the experiments, and this is what we get. So as you can see, this is the OH field. So white regions are regions of high chemical intensity. One thing to keep in mind right here is I'm showing H field for the numerical fields just to make it a bit more visually appealing, because OH, as you can see from the experiments, in detonation timescales lives for a very long time. So you have illuminated regions behind the front that are already past the reaction zone. Whereas if you see here, H grows and decays very quickly across the reaction zone. And this can be confirmed by just a simple ZND simulation to see that this is a good marker for the reaction zone. Whereas OH is a bit more spread, which makes, once again, one of the main limitations when you use it experimentally is that it could obscure or make difficult the analysis of the results. But the one thing to note here is that in terms of the topologies that we see, of course, in the OH signal, you see partly where, you know, strong chemical activity is taking place, and you see more in your numerical fields. Now, if we go further in time, we get similar topologies. But as you can see, these two diagnostics are complementary, because right here you can see the decoupling of the reaction zone and the leading shock as it moves across along the inner wall of the chamber. You have formation of strong chemical activity right there. So you see this became a Mach stem. And you have an interesting structure here that is strong chemical activity right behind that Mach stem. And you have another obliquely joint region of very strong chemical activity right here that, as you can see, is the fact that this little shock is actually propagating into something that was shocked but fresh, and it's a result of the decoupling that took place along the inner wall. And then you have this very interesting structure that we call it an S shape, which is simply that we'll discuss later, and is the competition of this rotating Mach stem and the transverse wave that propagates in shocked but fresh mixture. So you can draw your own conclusions with regards to the agreement that we have. With regards to now the higher pressure, 26, then of course, as you increase the pressure, you have detonations that are less sensitive to area changes, right? The area is increasing, but you do see interesting activity happening inside. And that interesting activity that is happening is all these triple points that are getting more and more spaced as they diffract, right? Then you have finally the decoupling, and then the transition from a regular reflection, as you can see, and then once this regular reflection meets the decoupled but shocked fresh mixture, a transverse detonation propagates through there. And then when we look at the comparison of these fields with with what the experiments show, we can see the areas of very strong chemical activity, the regular reflections, as you can see right here, very, very strong chemical activity right there where you have the regular reflection happening as you would expect it. Pretty much everything gets saturated by this, so you only see this very tiny white spot right there, part of the regular reflection, but you can't really see much of this other shock that is still part of that in the OH fields that we gather experimentally, and it just continues to propagate as a regular reflection. Now, this is what we get numerically in terms of soot foils. So we have this detonation that was propagating initially in that straight section of the channel, and then as it propagates, you see that you have strong decoupling, so which is signaled by the lack of cellular structure in this region. So you pretty much decouple the leading shock and the reaction zone, but you have a reignition that we'll discuss later. And when you look at the soot foil for 26, so the higher pressure we tested, you do see interesting increase of the cells along the inner wall and successive decoupling and recoupling and reignitions that take place inside the wall. So the increase of the cellular structure has been documented before and is a typical feature of diffracting detonations as well. But what's important to keep in mind here is that these soot foils will allow us to tell very nicely the exact location along the circumference of the transition between regular reflection to the Mach detonation that I described earlier. Same here. So this will be an interesting point of interest that we'll revisit later. So if you look at so we actually tracked the reaction zone and the front position at a frequency of 1 megahertz. So every microsecond we took, or we found where the position of the shock and the position of the reaction zone were. And the way I showed this right here, so if you recall what I had showed in the schematic, so this is how we measure angles. So we have, this is 0, and this is 180. Okay, so 0 to pi. So the detonation is propagating from here to here. So we propagate from the second quadrant all the way to the fourth quadrant. So if you look at this, we're propagating from 1, because this is normalized by pi, into minus 0.5. So we're going from the start of the outer wall, where we meet the initial curved region, into the end of the chamber as we move from left diagonally to right. So you see the shock front, the reaction zone. We tracked the max of H to pinpoint the reaction zone location. You see a region of decoupling right here. You see more interesting dynamics in the inner wall. As you can see right here, the strong decoupling between the shock and the reaction zone, then a reignition, then another decoupling. And then when you look at the wave speeds that we record in the same way, you see that in the transition between regular to Mach detonation, and then into that S shape, we see an increase of the steady propagation. And what we wanted to show is that you have, on average, right here, a detonation that is actually propagating above CJ. conditions. So it's actually an overdriven, steadily propagating front. And then if you look at 26, you have way more interesting dynamics taking place along the inner wall, as you can see from all these reignitions and successive failures and reignitions taking place along the inner wall. And then just another coupling, as you can see, of the reaction zone and the leading shock. And then the same initial increase and decrease as you go from regular to, excuse me, to a Mach detonation. Now, we're going to zoom into the early stages of the dynamics just to dissect it a little bit. So as I said, so initially you have your initially planar detonation. As it meets this part of the wall, then you start to see the formation of a Mach stem right here. And as you start to meet the increase in area right here, then you start to see initial decoupling of the leading shock and the reaction zone. You see all the triple points that are traveling along the wave. You continue to see them there. You see more clearly the formation of the Mach stem along the outer wall. And then you have this region of a fully decoupled reaction zone and leading shock. So this is a fully decoupled detonation right there. But then all these triple points that are bouncing along the front, there comes a point where they meet and you reignite a detonation inside the shock mixture, as you can see at 131 microseconds. And then you pretty much have a very strong transverse detonation that is propagating inside a previously shocked mixture. And then as this detonation propagates inside this region, it just once again reflects along the inner wall. And this is just some remnants of that reflection from the inner wall. Now, if we look at the flow structure, as I said, you have a curved detonation wave. Right here, you have a transverse waves. So that's just a remnant of one of those transverse waves along the front of these triple points that will get drawn. These are, by the way, temperature fields taken from the simulation. So these are actually a picture that I took from the simulation itself to describe what's happening here. Then a transverse detonation right here, a transmitted shock into this region that it's already burned. Then you have the decoupled reaction zone, the decoupled leading shock, and the shock fresh mixture right here. And then if you think, or if you're familiar with the flow structures of detonation in confined environments, this is a typical structure of that. So this is confinement by burnt products. This is a detonation that is propagating into this shocked mixture and a transmitted shock. So this is a very typical flow field or a similar flow field that you would encounter in detonation propagation under yielding confinement that if I'm not mistaken, Xiaosheng has worked on that extensively, or in one of the projects that he's been involved in. Now, if we look at the early stages of the dynamics for 26, as we can see, I mean, we don't really see much other than my detonation, or at 26, the detonation is way less sensitive to the area change. So you continue to have triple points that are bouncing up and down as you go. But you do start to see the same right here, the formation of a Mach stem along the outer wall, formation of Mach stem. Then you have remnants of those triple points right there, and then a slight decoupling. But as you can, if you recall from the video that I showed earlier, then this gets very quickly consumed by those transverse waves that then meet that decoupling that is happening here, and then it just consumes the mixture right away. And just in the same way as we showed earlier, as it bounces off the inner wall, then you just have a reflection that I showed there. Now, in terms of the the flow structure that we see is pretty much the same, except that the spacing between the decoupling is very small. But in terms of the type of structures that you get is the same. You have a decoupled leading shock, decoupled reaction zone. You have a region that is shocked but fresh, and then you have all these triple points and transverse waves that are going to run down and consume that as soon as they reach that area. Now, when we compare the decoupling, or the first instance at which these detonations start to decouple, you see that at 15, the coupling happens sooner along the inner wall, but later in time. Whereas at 26, it happens later along the wall, but sooner than what we observed at 15. And that is just tightly coupled, or is simply a consequence of the initial conditions and the differences in detonation propagation speed. So just faster wave velocity. But this has consequences and implications into the structures that we observe and the transitions between regular and Mach reflections along the outer wall. So the transition from regular to Mach reflection to an S-shaped wave. So as you saw in the videos, so right here you see we have a regular reflection reaction zone that is fully decoupled, and then the start of a transfer wave that propagates into this shocked but fresh mixture. And as you can see, you're going to have a front that propagates here, and then a front that is propagating along this curve right here. So in the end, what happens is that as the rotating Mach stem continues to propagate, it starts to compete with the propagation of this transverse wave. And then by the time it reaches the end of the chamber, you have this interesting looking S structure that we saw in the experimental images, that we now understand where it comes from, or what the flow structure and separation between shocks and reaction zones look like. Now, if you look at 26, then what happens is that later you have this transition from regular to Mach reflection into what I call a gamma-shaped wave that you see here. And it's exactly the same, but this is simply a consequence of the location where the transition from regular to Mach reflection took place. So if we had a longer wall, then we could actually get to the structure that we saw at 15 kilopascals as well. Now, with respect to the transition angle, so I only explained in detail 15 and 26. We also ran cases for 20. We didn't have any additional insight that we could gather in terms of the flow dynamics, wave structures from 20. So I only show 15 and 26. So all of this are detonation transmission into this curved chamber. And we have an additional case at 10 kPa that I will discuss later, in which we actually have not a detonation transmission case, but an ignition behind the Mach stem. So what we get from this, I'm plotting the critical transition angles. So that's the location where this regular to Mach reflection takes place. And as we increase pressure in the convention that I explained earlier, it simply happens at a later location. As I said, the inner dynamics is tightly coupled with the outer dynamics. So when you have that full decoupling plus the competition of the rotating Mach stem along the outer wall, then it's going to determine the location where transition between between regular reflection to Mach reflection takes place. So a function of, as I said, the leading shock reactions on recoupling along the inner wall, and seems to asymptote with increasing pressure. But in my opinion, this is simply a consequence of the fact that we have a chamber of finite length. So there's not much to be read on this asymptote behavior, in my opinion. Now, if we compare the late stages of the process with some experiments that we run at 15 kPa, we see that the structures are practically the same in terms of separation distances between the shock and the reaction zones. The shocked but fresh mixture that we have here and here, the separation distance between the decoupled reaction zone and decoupled leading shock, the shape, more notably, the shape of the wave that propagates along the wall. Now, one thing to keep in mind as well that I think it was an interesting finding, or it's an interesting analogy that we could draw from this, is that all these dynamics that we just described is in agreement with previous work that looks at transmission of detonation into an open volume. And right here, I'm showing a picture that was taken by Florian Pinkton at Caltech in 2004, where they see very similar structures as those we see, namely the fact that you have, as a part of the reinitiation process, that the coupling of the leading shock, the reaction zone, and these transverse waves, that not waves, but actually transverse detonations that propagate and run to consume that mixture that lies in between these two regions. And as you can see, I'm just simply showing some soot foils from previous work from my colleagues, in which we have the same. So we have this Mach detonation, cells that are very, very small, way smaller than the ones in the transverse detonation, that are just a signature of the transfer detonation that is propagating in that region that was shocked as a result of the coupling of the leading shock and reaction zone along the inner wall. And the other thing to note is we have same reinitiation dynamics, different geometries, different mixtures, different pressures, which leads us or suggests that this may be a universal feature of the reinitiation of diffracting detonations. Now, let's look at the 10 kilopascal case. In the 10 kilopascal case, as I said, we don't really have with the initiation scheme that we have, we don't really have a transmission of a detonation into the chamber, but rather a planar shock that propagates into a curved chamber. And then what happens is that you form that Mach stem that we discussed earlier. And right behind the Mach stem, where pressures are of the order of 25, the initial pressure, and temperatures ratios are the order of 5, the initial temperature, then you initiate a detonation behind an inert Mach stem. And once again, all the simulations were run. I did my numerical experiments, then I obtained this result for 10 kilopascals, and then I asked my colleagues in the lab to attempt to see what sort of dynamics they would observe. And for that, they had to make a bit of a change in the experimental setup, and that change was that before we had all this filled with reactive mixture, right? We only had this Mylar one that was just, keeping the expansion vessel separated from the test area. So what we had to do is to actually have another Mylar here and have the exact same detonation initiation that we had before. Now we had the detonation that interacted with this Mylar, and because this was still filled with reactive mixture, we had the propagation of a planar shock, inert, that would go into the chamber. So no longer a detonation, but a shock that would go into the chamber. And this is what we got. So as you can see, we have initially a planar shock, Now, as we go into the curved section, we have this very nicely formed Mach stem, and then we have an incipient ignition center right there that forms. And as you can see, the agreement with the experimental images is quite remarkable. And then the one thing to keep in mind that a lot of people have been discussing the importance of diffusive, of momentum diffusion and heat losses, especially when you have all these wall effects. It looks like in this particular case, chemistry is dominant over all these diffusive effects. Why? Because in the numerical framework that we use, we have an implicit computation, and we capture in very, very well, a very, very good agreement, the dynamics that we observe. So you can see here, as this ignition center grows, then it will overtake the Mach stem, as you can see here, and then you just have a detonation, a spherical detonation that propagates into this shocked mixture, and then interacts with this interface that was just the failure of the detonation that couldn't sustain at this pressure. And then you have this reinitiation. We have this very nice experimental pictures as well, showing the exact same dynamics, and now a detonation that takes over the whole entire chamber. And then a Mach stem that forms along the outer wall, a nice curved decoupled shock, as you see it here, and the same S structure, but with a bit of a kink right here. So we have a Mach stem, another wave that forms here, and then a transverse detonation that is moving along shocked but fresh mixture. So the question that we had is the wave dynamics only governed by geometry and initial pressure then? Because as I said, in the highly compressed areas, given the fact that the resolution that we chose is based on the steady Z&D length. So even if we have, for the lower pressures, we have close to 15, 18 points in our induction length, in taking as a reference the Z&D length, in the highly compressed areas, we clearly don't solve the cellular structure, which begs the question. So is this really governed by geometry and initial pressure? So then what we did is we tried to run an inert experiment. Instead of having a reactive mixture, we just run an inert experiment, and we have just an inert shock wave transmission. So we measure the propagation of this wave to be of the order of 1,000. We computed the pressure ratio. It's a pressure ratio of approximately 11. And this is what we get. So initially planar shock, Mach stem, and Mach stem along the inner wall. And this provides, not conclusive, but at least some substantiation to the conclusion, at least that or the question that arises when we compare all these results, given the assumptions that we made in the numerical methodology, that this is indeed driven by initial pressure and the geometry, all the topologies that we observe. Of course, the reinitiation transients and all these things will have to depend on the. You will not get them with an inert shock. Obviously, there's no reactions taking place. So just to close, Inner and outer wall dynamics, as I mentioned, are tightly coupled, and that determines the wave reflection and transition location, what I call theta crit. It seems to be an increasing function of initial pressure and seems to have an upper limit. But as I said, this is likely a consequence of having a chamber of finite length. The differences in the wave structure at late stages for increasing pressure are simply a consequence of the available arc length that we have. So it's the competition between the transverse and the Mach detonation lasts longer. So if it lasts longer, you get to these S shapes rather than the gamma shapes that we saw before. And as I said, the overall dynamics was predicted really as a blind exercise. Despite the low resolution, that we don't resolve the cellular structure in the highly compressed regions, which leads us to think that this is driven by geometry and initial pressure. So if you're interested in the overall flow features, there's no need to resolve the structure, and you can just do a simpler modeling or simpler kinetics or whatever reduces the computational cost, in case you're interested in simulating this type of propagation in curved geometries. And as we said, and we have already explored, well, the team has, I haven't really been involved in those efforts, have looked at geometrical shock dynamics, and that's something that we're interested in checking in more detail. And right now, we're also doing a more detailed study of the inner transmission of the shock waves and looking at the types of dynamics that we observe. And with that, I would just like to acknowledge the contributions of, once again, all the team members and the Institut Pprime, all the technical support for the experiments, and the School of Engineering, LANSMA, CNRS, of course, and the University of Poitiers. And some of this work was also part of an industrial chair that was awarded to the lab called Kappa, which was in collaboration with Safran and MBDA. And with that, I open the floor for questions, and thanks a lot. I hope I didn't went too much beyond the allocated time. I think I did.
Yeah. Okay, great. Thank you, Josué. This very interesting talk. Yeah, I already got 2 questions from chat. Okay. I will read you these 2 questions, and then we'll open the discussion to the audience. They can unmute themselves and directly ask to you.
Sounds good.
Yeah, the first question is from Dr. Wenhu Han. His question is, a detonation for hydrogen oxygen with a 40% argon dilution mixture is highly unstable. In the simulation, 5 to 15 points in induction zone length maybe not sufficient for convergence or valid result, especially when it run in geometry with curved boundaries. The simulation requires higher grid resolution. So I guess that's a comment.
Okay, well, then yeah. the question to him would be, based on the thing is, what are you interested in, right? And the other thing is, based on the results and the agreement that we get with in terms of wave separations, reaction zone, leading shock reaction zone separation, wave velocities, all the measurements that we do in terms of the stuff, of the results that we do and the comparison that we do with the experiment, one would think and that is not enough, but the results show otherwise. So it all depends. Are we interested in resolving the detonation structure? No. Are we interested in looking at the wave dynamics inside the chamber? Yes. Was 15 points enough? Looks like it was. And then if you look at, I would not agree that a H2O2 detonation with 40% argon dilution, is unstable detonation. I would rather use regular and irregular because all detonations are unstable. But a 40% argon dilution detonation is not a highly regular detonation. What is the chi parameter for that? I don't have it off the top of my head.
Yeah, I agree with you. I wouldn't say like a 40% argon dilution would make it highly unstable or highly irregular. I would say it's more like a moderately irregular or like more like regular, right?
Yeah, and by the type of, I mean, what we get in our soot foils, we get relatively, I mean, the sizes of the cells are pretty regular. So we don't get any inner structure with, I mean, we would not necessarily get, because one would potentially need more resolution for that. But there's no signs of irregularity in the soot foils. I mean, once you go into the curved chamber, then that's a different story, because you have diffraction effects. I should probably open my video.
I will go to the second question. It's from Professor Mike Kuznetsov. His question is about slide number 53. The question is, or the comment is...
Can you still see my...
Yeah, I'm still seeing your slides. Yeah. The comment is the time difference should be corrected to speed of sound at 15 and 26 kilopascal. The difference might be compensated.
Well, the speed of sound is rho RT, right? So T is the same. I mean, gamma RT. But I mean, there's definitely a difference in, I mean, it's not that a difference is compensated, or whether we were looking for this to be the same. We simply looked at or propagated a detonation in a higher pressure environment, and we get a detonation that propagates faster, as expected. And then what I wanted to highlight with this particular slide is that the place where this decouples governs the transition from regular to Mach reflection along the outer wall. But
it might be also it might be also governed by the proportionality of distance to detonation cell size also.
Okay.
Because for 15 kilopascal detonation cell size is a measure of chemical reactivity for detonation. So for 15 kilopascal detonation cell size is bigger than for 26.
Yeah, absolutely.
Okay, thank you.
Yep.
Yeah, I just saw a quick comment from Professor Andrew Higgins. He said the chi parameter for H2O2 with 40% argon dilution is about 1. Right.
So it's pretty stable, right?
Yeah.
Thanks, Andrew.
Yeah. And I saw Xian turn on his camera. Yeah, please go ahead.
Sure. Yeah. Hi, Josué. This is Shen from Stanford. Thanks for your presentation. Hey, the close agreement between experiments and numerical simulation is remarkable. Great work.
Thank you.
I just have a few questions. The first question is, by looking at the synthetic soot foil from the numerical simulation, it seems that the detonation wave, when it enters the curved chamber, still carries a lot of memory from how you initiate the detonation. I guess what I mean by, let's see, for the 15 kilopascal case, the cell size at the entrance of the curved chamber is not the cell size for a sort of steady state 15 kilopascal propagation in like a long tube, right?
Well, this right here is how we initiate it, okay?
Right.
So this is not and then our metric, my metric here. So one thing to keep in mind is that the detonation cell sizes with detailed chemical kinetics, you typically underpredict these detonation cell sizes as compared to what you would get with the typical NG parameter and all these things. So the ratio between the experimental cell size and the numerical cell size is about 3. Okay, one thing to keep in mind. Now, the other thing to keep in mind is that the actual dependence of the cell size with pressure, we capture correctly. So how the percentage of decrease, okay? The absolute values are not the same, but the percentage at which, or the how it should decrease with pressure, we capture properly. Now, if you look at this, so the detonation DCJ for this mixture is 1,998 or something like that. I can confirm that if I open this. And that's the value that we get as the first point in our wave speed measurement.
Yeah.
So it looks like even if, and I think that what throws you off here is the fact that there's a transient in the initiation, and that you may think that you may still carry memory by the time you get here. When you do measure your speed, it's CJ.
I see.
Right there. Yeah.
So I guess regardless whether the steady state cell size is comparable to experiments, can you comment on, let's see, if I actually have a transient entrance, would you expect a similar sort of dynamic happening?
You know, I would think that even if your detonation is overdriven, or I mean the physics of the expansion will not change. So you have an area increase, you have expansions that start to fly and propagate along the front. Then you have a decrease in pressure, you have chemical kinetics that is very sensitive to temperature, and then you quench reactions, and then you will have a decoupling of the reaction zone and the leading shock, and that's really what will be the physics happening, regardless of whether your detonation is slightly overdriven or not. Now, what will happen is what I show for higher pressures, right? If you go towards higher pressures, then the area change or the expansion will be more or less sensitive to, I mean, your detonation will be more or less sensitive to your expansion, because it's able to recover quickly from the fact that your rate is decreasing right behind the leading shock, which is what you see here, right? All these are all those triple points that are traveling along the front and are just going, and wherever you see a decoupling, boom, it goes and consumes it.
So those oscillations are actually from the inner wall, sort of.
Yeah. So these ones are inner wall oscillations, and this is the outer wall measurement. And then you see it here, right? So pretty much what I'm showing in the plot below, it's all this interesting cellular dynamics that is happening here. It's all this continuous and successive quenching, reinitiation, quenching, reinitiation, quenching, reinitiation, quenching, reinitiation, until full decoupling takes place.
Right. Yeah. Oh. Okay. Yeah. Thanks for.
Thank you. Thank you for the questions.
Actually, just a quick additional question on this. I guess by looking at this geometry, it reminds me this sort of innovative RDE where there's not a central body. Essentially, you only have that.
So I might have not mentioned that, but that was the main, one of the motivations of the work was to try to contribute a bit towards the understanding of what they call the hollow RDs.
Right. Yeah. I guess based on what you learned so far, can you comment on the operation feasibility of that type of RDE compared to the traditional RDE?
Well, I mean, apparently, as I said, my interest was to look at the wave dynamics inside, right? So I would comment on what I know and what I've read. Apparently, these provide better efficiencies, and it's supposed to be a promising alternative. I mean, based on this, I mean, we do understand a bit more what's driving at least the reflections and the wave structures inside. Whether this is better than a fully confined or just two concentric cylinders and all that, I admit that I don't know enough to speculate on that.
I see. Thanks.
Yeah. All right. Thank you.
Yeah. Thank you, Xian, for your question. I got another question from chat from Dr. Minbo Long. I don't know if he wants to unmute himself to directly ask, or he prefer me to read. Maybe I will just read. Yeah, his question is, Euler equations have been widely used for detonation simulations, neglect the effects of diffusion. I wonder, can we use it for cases with weak turbulence? Which criteria to determine that we can safely use Euler equations? Yeah.
Well, which criteria to safely use? I mean, I guess that the way of looking at this, or at least the way I think about these things, is before adding too much, I try to simulate with the simplest I can, right? So weak turbulence, I mean, arguably one does have some level of turbulence inside this chamber, right? Now, with respect to wall effects and momentum diffusion and heat transfer and all these things, I would say that based on the agreement that we get, it seems relatively safe to at least if you're interested in wave velocities, like overall structures and things like that, yes. Now, if you want to look at the topologies of the flame and things like that, as you can see here, right? Even though this is a bit, this is integrated and all that, this experimental image, the flame does have a structure there, you see? Whereas my flame is really, it's just a planar indication of the reaction zone, but there's definitely something that we failed to capture with the implicit formulation. Now, whether it's important or not, I would say that we continue to be relatively safe to simulate it with another description of or with an implicit description for what's happening here. So wave velocity is fine. Separation distances looks like we're fine. As I said, arguably we have some level of turbulence inside at the start of the experiment that we don't have in the computation itself. Yet we capture the global features and very transient features as well, like reinitiations, diffractions. So I guess that's just my reflections on that. It may not be a full answer, but at least things to think about.
Thank you for your answer, and thank you for Minbo's question. Is there any further questions or any other comments from the audience? Actually, yeah, sure.
Mike, I have one more question.
Yeah, please. Yeah.
Jose, you concluded about the governing role of initial pressure on dynamics of the detonation diffraction in annular channel. But it makes hidden the real governing parameters. I mean, the detonation cell size and chemical length. And I think that it's very important ratio between detonation cell size and chemical length, and because the dependence of chemical reactivity and detonation cell size on pressure is different. So
yeah. No, I don't disagree. I don't disagree with that.
yeah,
So
and so if your reaction order is less than 2, like for propane, then the chemistry will be suppressed by higher pressure.
yeah,
But the detonability, which the measure is detonation cell size, will be inversely proportional to the pressure. So then it will be different behavior at higher pressure. I mean, the ratio of lambda to delta, which is the chemical scale, will be different. And when it will be the same order of magnitude, then the probability of decoupling of detonation front and value of detonation is higher, then it will be at larger ratios of lambda to chemical scale. This is my comment or question.
yeah. No,
I mean, you didn't operate in terms of chemical scale or the detonation cell size because you have a nice tool like CFD code, and you can demonstrate visually the difference. But if you would operate in terms of some criteria, then you need some parameters, not the pressure, but some physical, chemical parameters. This is what
yeah, I mean, and one of the motivations for us to do this type of study where we could actually, you know, resolve the chemical kinetics with you know, some degree of confidence was precisely to determine that is really the chemical kinetics governing the wave dynamics inside.
Yes.
And my answer to that, based on my results for this particular mixture, is no.
Mm-hmm.
Chemical kinetics, as what we show is we don't resolve the cellular structure inside, right?
Mm-hmm.
We do capture the proper delay times. You know, each cell, depending on its thermodynamic state, it gives the delay time that you would get from a detail mechanism that takes into account the changes in pressure, temperature, local, all these things.
Mm-hmm.
But we do not resolve the cellular structure inside the highly compressed areas like this, as you can see it from the soot foils, right? So, which leads us to conclude. So you see right here, in a real detonation, in a physical detonation, you would have this full of little cells, very small cells. Same here, very small cells, right? Which is what I actually show here, right? So there's very tiny cells right here, there's very tiny cells there. Do we need the cellular structure to capture the dynamics? Our learning based on our results is no, at least for this mixture. Do we need to capture the proper delay times so that my cells react and the coupling between the gas dynamics and the heat release is adequate? Absolutely.
Okay, Jose, I agree with your arguments, but the chemistry efficiency would be more visible if you would change the fuel to, for example, to ethylene with reaction order of 2 or to hydrogen. Then the reaction order will be higher than 2. And you will see the trend, how it behaves at higher pressure with chemicals with different reaction orders.
Okay, with different dependence on pressure.
Yes, yes,
okay.
Yes. So
Taken.
this is
That's a good point to take into account. I mean, I guess based on these learnings,
mm-hmm.
what we can say now is, look, maybe a detail mechanism may not be necessary, but we have a simpler description of the chemistry where we take into account this pressure dependence for a fuel like ethylene, as you mentioned, and then see what sort of dependencies or what sort of trends
Yes.
rather we get as a function of pressure. That's a good comment. Thanks a lot, Mike.
Thank you.
Yeah, I actually have a further comment on this. I think maybe it's I think the statement you made that the overall dynamics is not very sensitively influenced by the kinetics. I think this statement might be restricted to this regular mixture or like a weakly unstable. Yeah,
perhaps.
I don't know. Like I think you probably have already done like maybe some even higher resolution runs. Like if this does show like a perfect numerical convergence, that means like even you are resolving those like small cellular structures, those transverse waves or the triple points are not like the dominant factor for the reaction rate, right? It's probably just like very weak. Visually, you see these transverse features, but they are just very weak waves. So the overall combustion process is still like governed by the front shock triggered initiation.
Yeah,
right?
Absolutely.
Yeah, I think like maybe like if you do like some highly unstable or more irregular mixture, this might be a different
So
qualitatively different answer.
Some of the results that we get with propane lead to similar conclusions in terms of, I mean, it's only experimental. I mean, I haven't attempted to simulate a propane mixture with detailed chemistry. We can't really do it. At least I can't with the code that I have. I mean, I could, but it just take forever. The conclusions from this work and the conclusions that we got, and as I said, the reason why we chose this mixture to be the mixture that it was, is to see if we could get some feel about what's really governing the dynamics and whether we really need detailed chemistry for this. It may be too much of a far-reaching argument, perhaps, or a bold comment to say, oh yes, it's only geometry and initial pressure. We've been doing some inner shots that seems to be the case, or at least to support our findings. We have to definitely see if what would happen with a more irregular mixture, and then also the comment that Mike made regarding the different sensitivity of some hydrocarbons for increasing pressure. So those are good ideas to explore.
And also, I find it's very interesting remark you made that this transverse detonation is like a detonation under the yielding confinement, right? Yeah. I think like if this is like experimentally, if this is very controllable and repeatable practice, then this might provide a better or like a more well-controlled way to study this phenomena, because I think like there are some like like old school experimental works that try to study this detonation under confinement in gas phase, but they always have some disturbance on the interface, right?
You need a miler, you need something to divide the interfaces. Well, could be. I mean, as you can see here, I mean, you see that same structure.
Yeah, because this might be a side product, but actually this phenomenon is quite similar to what happened in RDE, right? I can imagine like this.
It is. So if you were to, let's see if I can do this here. Can I rotate? Yeah, right there. You see, from right to left. So this would be an RD right here.
That's very interesting.
The confinement, then the detonation propagating into this.
Right.
Yeah. That's right.
Yeah. Yeah, because without this geometry, this diffraction geometry, like I think in normal unstable detonations, you have a little bit of this phenomena going on, but it's not that exploded, right? Like this is more like you just stretch this phenomenon to make it like a visually more accessible to people. So I think this, yeah, just this to me is very interesting phenomena that people.
It's definitely food for thought. Yeah.
Yeah. Yeah. Yeah. Thank you. It's very interesting.
No, thank you for the invitation.
Yeah. And thank you for your time. I believe it's almost the time to end.
It's almost time to go for dinner.
Yeah.
At least for me.
Yeah.
No, but thanks again. I enjoyed it, and I hope it was good for those attending as well, and look forward to more of this. And thanks once again for really taking the leading role in this, because this is nice. It's nice to interact, to discuss with everyone, you know, to hear Mike, to see you, to see Andrew as well, to see Sham from our Stanford friends, everyone. So all right.
Thank you. Yeah, thank you very much for your time. And just an announcement for next week. Also on Monday, we have our next speaker is Yaroslava from Moscow, and I will distribute the brochure of her talk in a timely manner. And after we edit the video for Josué, we'll send to Josué for approval. And after that, upon getting his consent, we'll upload that to YouTube.
Great.
Right.
Thanks a lot.
Yeah, thank you all for your time.
See you guys later.
Yeah.
Thank you.
See you.
Bye-bye.
Have a good day or good night.
Well. Bye.
Bye.
Thank you.